Okay, so the tutorial 6 and homework 6 are due next week. Tutorial 6 is due next Friday. So since Monday is exam, so I don't think I should start a new lecture. What do you think? It's due Friday, so I can go through some of the older problems, and hopefully you can practice on these ones to prepare for the exam on Monday. Yeah, cool. So Monday, tutorial 6 is all about amplifiers. I think it's easier on calculations and algebra, but concept-wise, it's even more trickier because a lot of people, even electrical engineering students, when they graduate in the senior year, still don't know what op-amps is, how op-amps works. But I think I can do my best to let you guys understand what's going on, and tie it with some of the practical applications. It's easier to understand. Any questions on the exam? Any problem you want me to go through? No. But I still should do that. It's really interesting. It's the most important technique, I think, in Circuit 1, but it's only covered for one problem in Homework 5, and it's not covering the exam. What's that?
On some of the practice exams, it said like what method you should use. Will the
Yeah.
questions
Yeah, I printed it up. Yeah, let's see. Which one? Which one?
It was the fall 22 question 6, but it just said like will the questions.
It doesn't have question 6, it's question 4. Oh,
The fall 22, but it was the other practice.
oh. Did I print it out? I didn't. Which method you should use, right? I don't think the exam will ask the question like that. I don't think so. Should we open it up and take a look at it? Right.
Yes.
So let's take a look at these ones, the practice exam problems. So the first problem on exam is very similar diagram showing you a black box and having currents and voltage labeled, but doesn't have this kind of calculation involved. So it's just a lot easier than this. It's just a polarity sign convention stuff. You make sure you understand how to deal with that type of problem. Could you do that? I think, was that on Monday or Wednesday? I give you a lot of examples. I listed all the combinations of the polarity and voltage and currents, remember? If you still couldn't do it 100%, then go back to the notes and video. Make sure you understand that. It's 10 or 20 points, the first problem. Okay? So it's giving you the voltage signals, you know, as a Circuit 1 first, for all the beginners, trying to scare you. These are just numbers, right? It's a function of t. That's it. Doesn't matter what that looks like. It's just a function of t. It's just the voltage changing upon time, right? It's not a line. It's an AC signal. So got a V, got an I. So the first question is find out power, because both functions are the function of t. So you got V and I, V times I, you got a power. And plug this in, that's it, right? See, V times I, V times I. This times this plus minus this no, this times this minus this times this minus this times this and plus this times this, right? That's V times I. And plugging this time in it, you're getting this. That's the power. How much energy delivered to the circuit element between 0 and this? 125 microseconds. So power, energy. Energy is a integral of power, right? So integrate this equation here. of this expression here, plug this in. See, it's duplicated in here. And integrate. Integration, it's calculus 1 problem. So that's the final result. That's the power consumption or energy at this time, right? So that's the final result. And find the total energy delivered to the element. Total energy. Oh, actually, this is the energy at this time point. So this time, plug in the t's here, here, and here, and you are getting this number. Okay, you're getting this number. And you do the integration, you are getting this number, right? Wait, did I make it? How much energy delivered to the circuit element between this time frame and the total energy delivered to the element? What's the difference? What's the difference though? Oh, this is the energy at this point.
It's at times 0.
But oh, minus 0, right?
The total energy is at times 0.
Yeah. So you plug this number in here, you are getting this, right? Okay. If you do this, you are getting this. Am I right? What did you say just now? Maybe you are right. What did you say?
It looks like for energy function, our at times 0, our energy would be equal to whatever W total is, our total energy. I don't know why that's happening, but is it because it's
Oh no, because these numbers are the same. So if you put a 0 here, do you want to do the calculation? Let's just do it. Okay, let's don't skip it. Let's do it. So this is omega or W. Let's say W. WT. Okay, WT. So you plug this into here. You know what I mean? So let's just give you the conclusion. I calculated. If you plug 0 here, and these numbers combined is the same number as this one, just by chance. That's why. But let's calculate it. 625 microseconds, which is giving us 140.625 minus.
Yep.
That's right? I mean, should we really calculate it? Like this takes a lot of time. Let's don't do it because this is not on exam. So let's don't do it. So this is apparently this is plug this number in here, right? You are getting this, and this will be you plug. So this is 625 microseconds and 0. You have to plug this in here and minus 0 in here. You know, that's for integration, right? This number is just plugging 625 microseconds in substitute t in here. That's how you get this. Okay, to get this total, you have to use the integration, which is t and 0, right? So t is this, 0 is you plug in zeros. You got two different numbers, and subtraction you got this. Okay. Don't take too much time on that. It's not being examined. The second problem. It's a good practice, okay? So for this circuit below, if you look at this circuit, you see a wire at the bottom, you got scared, right? What's going on? Doesn't look like a normal circuit. Okay? What's the first step? First step, calm down. Don't get scared. Super simple, right? Why simple? How do you want to do it? You are thinking like trying to recall all the node, mesh, superposition, and trying to figure out, right? Equivalent circuits. It's basically just this voltage, two resistors, you got a voltage here, Vx, plug in, done. You don't even need to do all the things here, right? Let's see if that's true. Don't look at this thing. It's just a zero, just ground. Okay. You're thinking this scares me. What is this doing?
Just transferring your voltage.
Yeah, transferring, or just having a, what's that called?
Ground.
A common ground. You need a reference, right? So all the different circuits, you need a reference. I can give you another example for you to think about. Sometimes, for example, I have a circuit board. I can have a circuit board here. Embedded systems, right? It's a microcontroller. It's another class I teach at Mines. It's a really good class. Take it. lec18 It's a microcontroller board. Has a little CPU here. Has like analog digital control modules. Has PWM. Has a lot of GPLs, I2C, SPI, UART. A lot of functionality integrated into this microcontroller, and you can control LEDs, control motors, control lights, whatever you want to do. Okay. And communicate with the boards, with the computer as well. So you can see this is a floating. It's a floating ground. So the board definitely has a common ground with all the components on the board, right? We know we have to have a common ground for all the circuits. So they do have common ground being shared by all the components on the board. However, when I want to communicate with my laptop, I plug in a USB port, right? A USB port like this, and I plug it into the USB port of the laptop. This starts communicate. Okay. Something you have to know: the ground or the 0 volts reference on this board has to be grounded, has to be shared with the common ground of the laptop's motherboard. How that works? Even though you couldn't see it, but in your mind, have to imagine there's a wire, is 0 volts, being shared by this and my laptop. How did I do that? I just have a USB, right? I didn't open it up from the back and have a wire to short it. How that works?
There's a ground wire in the USB.
Yeah, the USB has a ground wire. USB have power, ground, data lines as well. So you plug in, the ground is being shorted to the ground of the laptop. So you need a reference. So sometimes if I have two boards, right? Two boards like this, and I'm trying to communicate in between these two boards, and I have a data line here, power line shared, and keep in mind you have to have the ground line shared as well, or shorted to each other as well. That's a very common issue of student design. I've seen this issue 100 times, and 80% of the chances is the missing of common ground. Whenever I start debugging a circuit for students, anywhere, anytime, the first thing I check is if there's a common ground, because 80% of the problems is the missing of common ground line. Keep that in mind. So you have to find out the ground line, right? Short it, just have a common ground so they know what is 0. So 0 is 0, right? Otherwise, you have, for example, this board is operating between assuming this is 0 volts, 5 volts. Okay, for this board is operating here, 0, 5. They are both working across the two power rails, like 5 to 0. So it's working individually, no problem. However, if you bring them together, if you don't have a common ground, 5 volts here is being treated as 0 volts or something else. Okay, so you have to bring the common 0 to the same voltage reference. So 5 volts here is being treated as 5 volts on the other board, so they can communicate. You send the 5 volts, it sees the 5 volts. You have to have the same baseline, same reference. Okay, so this is the same reference, right? So it's shorting both circuits. It's not communicating anything. It's not affecting anything from here to here. Why? Like I said, it's the one voltage node. It's one wire. Okay? You can always imagine that you can heat it up and melt it. So it becomes one joint. Alright? It's just the one metal wire. Just one metal piece. So what's happening is you see Vx, for some reason, it could be some magical electric magnetic field. Vx here is affecting the current here. So this current source becomes a voltage controlled current source, right? It's a voltage controlled current source. It's an arrow, so that's why it's a current source. Is this current source being affected by this voltage through this line? Nobody tells you. No, it's just a reference. Keep in mind, it's just a reference. Ground line. That's it. It's affecting this one using some other methods that we don't know. The problem just tells you, okay, no matter what this voltage is getting, you divide by 10, it's going to be the value of the current for this current source. That's it. That's the only thing you need to know. Nothing else, okay? Don't get scared. So in that case, we have a DC voltage here. We got 2 resistors. It couldn't be easier. It's a physics 2 problem. Can you get a voltage here? Of course. How? A voltage divider, if you want, 20 volts times 150 ohms on the top over 450 plus 150, right? That's the voltage divider theory we have been using all the time. If you are not comfortable with that, which is okay, because sometimes you make mistakes. Why? Let me give you an example here. R1, R2, R3, okay, V, and these 2 resistors share the same VL. And you so doctorally running voltage divider theory in the class all the time. Start thinking, hey, just looking at this loop here, this mesh here. So VL, because he has been doing this all the time, right? Usually he has 2 resistors in the circuit, V out, R1, R2, V in, right? So VL equals V in times R2 on the top and R1 plus R2. That's the voltage divider theory he has been using all the time. Now you see similar structure here. Okay, so I got VL equals VI times R2 over R1 plus R2. What's the problem? What's the problem here? R3, yeah, but the fundamental problem here is R2 and R1, they don't have the same current. They don't have the same current. Do they have the same current? Current flows in here being split into 2 branches, so they don't share the same current. Why we care about that? So where this comes from? Looking at this circuit, you got 1 current. Okay, you times that current on top and bottom. What is this giving you? So this current times R2 is giving you V out, right? So V out equals R2 times I. And V in equals R2 plus R1 times I as well. So that's V in. That's the overall resistance times the overall current, the same current, and it's giving you V in, the total voltage. So because they share the same current, that's why I can cancel it. Okay? And then I can move V in over here to get the voltage divider theory or voltage divider equation. Because I cancel that current. However, these 2, R1, R2, they don't share the same current. So you cannot use this equation anymore. So what you have to do is you have to combine these 2 resistors. So that becomes R2 in parallel with R3. That's going to be the R2 here, right? These 2 combined is effectively R2 here. And at the bottom as well, you have to do R1 plus R2 in parallel with R3, right? Okay, but here, do they share the same current? Yes, just one mesh, one branch. So definitely can use the voltage divider theory to find out the voltage here, which is Vx. Okay, so when Vx is calculated, I just plug in here. It's just one variable. So Vx divided by 100 is giving me this current. So I can calculate the current. If I get a current, the current flows through this 300 ohms resistor, I got a voltage V out. You don't even need the KVL and all these. I don't even want to look at it. All right. Make sense?
Did you combine the 450 ohms and the 150 ohms and then treat it as like that being parallel?
They're not in parallel, they're in series. It's one loop. This is the ground. It's flowing back to the cathode. Why they're in parallel? So you got scared by this wire, right? That's why. Always look at this wire. It's just the ground. It's just the reference. It's a reference. You just melt it. Melt it becomes one node, one piece of metal. Oh, you are thinking if current is flowing out here, right? Is that what you are trying to say? Hmm?
Yeah.
Why is there's no current flowing out? It's the same voltage node, right? How do I explain that though? There's no motivation for the current to flow out. It comes back to the cathode, which is more attractive for the electrons. Or electrons is actually being attracted here, but just looking backwards, the current will go back to the cathode directly. And if you melt it, it's just the one node, right? It's not really. That's a good question, actually. So if we have, remember sometimes we look at the circuits, they have a wire in the middle, right? Like this. Whatever in the middle. You have a resistor here, and when we are doing KCL, we always assume a current here, right? But why it's different here? Let me find a way to explain that to you later, okay? Next time. But I think for this case, we find out the voltage here, and then we plug in, we got the current and got the voltage here, okay? Or if you don't trust this method, we can also use KVL. Let's try that. Starting from here, it's one loop for KVL. We assume an I here, okay? So that's negative 20, starting from the negative sign, plus I 450, plus I 150, you are getting 0. Okay? KVL. But you are still assuming the current flows back, not flowing here, right? I'll explain this next time. I'll find a way like how we can prove that it's not flowing there, okay? But this problem, I think if you follow KVL and use whatever the method I introduced, it should work. Okay. Let's look at the next one. Use the node voltage method to find out V1, V2 in the circuit below. Node voltage. One current goes in and 2 comes out. Okay. So for this node, definitely we can get 6 amps equals V1 over 40. V1 over 40 is the current flowing down, and then the current plus the current flowing to the right. V1 minus V2 over 8. Okay. For this node you merged it, you melt it and merge it. It's just one node. It's just one node. And the way to look at it is, for this one single node, you have 1, 2, 3, 4 branches connect to the node. So after you melt the metal and merge it into one node, it becomes something like this. Okay? So let's just list the one KCL. Can we do that? Why we don't want to list the 2 KCLs? Like you have one node, 2 nodes, so you have to assume a current here as well. It's eventually get cancelled, right? Okay? Let's just melt it. It becomes one node. So why is it called node voltage? What does node mean? Node. if they are shorted together, no matter how many branches, you got a wire, you got like millions of branches, right? It's still one node. Could you understand that? It's just one metal piece. So you can always imagine that you can melt it and it becomes just one metal piece. Okay? That will simplify your calculation a lot. So now let's do it. Melt it, becomes one node, right? Merged, so this shrinks, becomes one node. Okay? So this is flowing out from the node, and this is flowing out as well. Let's assume it's flowing out. Okay? Okay? So what we have here, one is flowing in, just only single one is flowing in, which is V1 minus V2 over what? Over 8. Okay, it's one single current flowing in, and looking at the melted node, you got 3 currents flowing out. So what are the 3 currents? V2 over what? 80 plus 1, right? So 2 equations, 2 variables, you can definitely solve for V1 and V2 easily, right? So look at this, it's the same. Right, same. So this is flipped, okay? It's the same thing. Right? Same. Any questions on this? So how to find the absorbed or delivered power? Does anyone still have questions on that? No? Let's pick up one. So assuming that we already calculated, V1 is 120, V2 is 96 volts. All these kind of problems regarding absorbing or developing power, it's in at least 2 problems on the exam. Even though they are not just asking for power, deliver power, absorb the power, but it's integrated into the problem. So you have to understand this, okay? So make sure it's clear today. I'm going to ask you questions, all right? Is this one absorbing or developing power? Do you need to even think about it? No, it's a passive component. It's always absorbing, right? Is there a case that any chance that a resistor can developing power? No. Why? Huh?
Negative resistance.
Negative resistance. Superconductors is not absorbing or nor developing, right? Superconductors for quantum computers. But what's a negative resistor? That's interesting. It's a power supply. All right. So you'll deliver a current to it. It sends out more current. There's no way that a resistor can develop power, because whenever you run the current into it, it creates a drop. So it's always pointing into that anode terminal, right? So what about these 2 sources? So we're assuming this is what, 0 volts. Now we're getting 120 volts and 96 volts. So for this power supply, it's having plus minus 120 volts. So it's developing because it's flowing out from the anode. This guy, it's absorbing. It's flowing into the anode, so it's absorbing. Make sense? Okay. Any questions on this? Cool. This one. You use mesh current method to find branch currents in IA to IE in the circuit below. Mesh current method. Oh, that could be a very simple problem because it only has one dependent source involved, and way easier than the ones you have seen homework assignments. So it's assuming I1, I2, I3. or clockwise. So if we start from here, that's negative 100 volts plus I1 minus I2. I found out that most of the problems are not in circuit analysis, it's in algebra. So I'm not the person to blame. Blame the high school teachers. Right? You're always able to list the correct match current equations. But the calculation is the place you get the errors. So minus 100 volts plus I1 minus I2 times 5 ohms plus I1 minus I3 times 10 ohms plus I1 times 2 equals 0. For I2, we're having I2 times 2 plus this voltage drop VCS plus I2 minus I1 times 5 equals 0 as well. And here, starting from here, I3 times 10, I3 minus I1 times 10 minus, see a minus sign first, so minus VCS plus I3 times 20 equals 0. So got 4 variables. It's telling you that the current here is 1.2 IB. What is IB here? IB is I1, right? So this current, which is I3 minus I2, equals 1.2 IB, which is 1.2 I1. So got 4 variables, 4 equations. You can solve for everything in the circuit. Check the solution by showing that the total power developed in the circuit equals the total power dissipated. So since all these resistors are consuming power, so they're all absorbing, and this dependent source is definitely, I don't know actually. So, it should. So this independent source, because you don't have other sources, so you can predict that this guy is definitely developing. And this one you don't know, so you have to calculate the current to find out if this guy is absorbing or developing. So in that case, you still have to find out all the currents to calculate the power for each component, and then see if they add them together, see if they are getting 0. Okay. Any question on this? No. Not too bad, right? I mean the exam, the real exam, is even easier than this. So don't worry too much about it. Superposition, we still have to cover it, because I think we may need to use it for op-amps, and it's just such an important concept. They spend so much time on the things that are not really being used, but super important things is not covered too much, which is weird. Let's go through this problem real quick, okay? .5 amps, 1 ohms, 6 ohms, plus minus V, 2 ohms. Yeah, even though it's not on the first exam, but could be on the second one, right? It's just something you have to know. It's on homework 5, it's already due, but past due, but so nobody cares, right? Just don't check out. Do you want to still see how that goes? Okay, cool. Oh, I love you guys. Cool. So proud of you. Nice. Superposition, you can use superposition to calculate, you can superimpose voltage onto each other and currents as well. Let me show you how that works. 26 volts, V1. Okay. So apply one source at a time. Okay, so first, call this I, this is V1, I1. So I1 only, it's going to give us the following circuit. If you only apply this current source, all the voltage sources, ideal voltage sources or independent voltage sources should be shorted. It's like a wire, okay? Because you are looking at each source, independent sources contribution to the circuit. So you apply I1 first. Short this guy. Okay, when you only apply I1. 4.5 amps. 1, 6, 2, 12, 4, shorted. So here's V. Okay, and then current goes in and being split into two branches and comes over here and split. So eventually it comes back to the source. Okay, so combines these two, it's a parallel resistor. So these two resistors gives you 4 times 12 over 4 plus 12, which is 48 over 16, which is 3 ohms, right? 3 ohms. So replace the whole thing here with the 3 ohm resistor. Two, 6. So you have to combine it, even though we have to split later, but now we have to combine all the resistance in order to get the total voltage. Why? Because this is the main branch current, 4.5 amps. So you have to find out the overall resistance here, like a black box. So you can calculate the voltage here. And what is the resistance here? That's 1 in parallel with 11, right? Which is 1 times 11 over 1 plus 11. Okay? So the voltage here, V equals, let's say V1 equals 4.5 amps times 11 over 12. .5 times 11 over 12. 4.125 volts. 4.125 volts, which is the voltage here, V1. Also is the voltage here as well. Can we use voltage divider theory now? Why? It's one current. It's one current. See? Remember we did that. I want to slow this down a little bit because just want to make sure everyone knows how to do it. If you know the voltage here, you got a resistor like this. It's a voltage divider. So you can calculate the voltage here by using this equation. If you're not comfortable with that, you can find out the current first and then times the resistance to get a voltage. So now we know the voltage here, same node, it's same voltage here as well. Okay, you got a voltage source, just assuming there's a voltage source, and it's the same current. So what is the voltage? V. Five. Okay. That becomes 5.125 times 5 over 11, 1.875 volts. You are not done yet. That's the voltage contribution from the current. Okay? Voltage contribution from the current source. Now let's look at V only, the V only version. Here. Oh, did we label multiple V1s as V1? So this is V2. VI. Okay, so V1 only. Current source should be disconnected because we only apply the voltage source in the circuit. Let's call it VV. Disconnect it, just remove it. So the resistance, let me see how we want to deal with it. Okay, here, let's calculate this voltage first. So if you look at this circuit, you got this black box here, becomes one resistor. So this is 9 in parallel with 12. It's giving you 9 times 12 over 9 plus 12. .14 ohms. Okay, so the voltage here, let's call it V3. If this whole black box can be replaced by one resistor, you just form another voltage divider here. Again, you got voltage source, voltage resistor, another resistor. Right, so it's another voltage divider series. You can get V3. So V3 equals V1 times this resistance in the black box, 5.14 over 5.14 plus 4 ohms.
Could you like draw what that looks like with the V3?
Oh, yeah. Right, here's V3. Oh, I know why. So it's still confusing you. You got a long wire here. It just melted. Melted becomes one node, right? It's just one node. So the whole thing, if you just look at these two terminals, the whole thing here can just be replaced by one resistor. It just these two terminals. You imagine you can cut it. You can cut it from here and replace the parallel resistor into one. These two are in parallel because it's getting split. And this comes back, you melt it, right? Just one node. So they merge, the current merge here, and then comes back to the source. That's why these are in parallel. So it's basically 12 and 9 in parallel, right? And just give you 5.14 if I calculate this correctly. And it's another voltage divider theory, so I can get V3 equals this. And this is basically 26 times 5.14 divided by 9.14. 14.62, which is V3, right? But it's asking for VV, right? So VV is another voltage divider theory, another one. So you know V3 here, right? V3. So it's another voltage divider. Why? Because you imagine this is V3, and you have a 2 ohm resistor, and you got another 7 ohm resistor. So it's asking for VV here, right? It's another voltage divider theory, right? Same current. Combines these two as a 7 ohms. Okay, 2 ohms, 7 ohms. The voltage got divided. And how to calculate the divided voltage is you have the voltage source here, which is V3, here. It's voltage across these two terminals. And just apply this again. So it's V3 times which over which? 7 over what? 9. And that becomes 14.62 times 7 over 9. 11.37. And now I have to superimpose onto the VI we calculated before. So let's draw a conclusion. So the overall V is VI plus VB, which is 1.875 volts plus this guy, 11.37 volts. That's giving you a number here, right? So superposition can be used in so many different places. And it's very useful and very handy. Just give you another quick example, still have 2 minutes. And you can use this method to verify your results easily. So you have some problem like this, right? I already gave you examples like this before. Oh, this is the DAC. This is a digital to analog converter resistor adder here. So you have V1, V2, V3, V4, R1, R2, R3, R4. What's the V here? So definitely you can use mesh, right? Mesh 1, mesh 2, mesh 3, mesh 4. But actually it's all the voltage contributing to this node and giving a total effective voltage to this node. So what you can do is, like, for example, V1 only, right? V1 only will give you this. Shorted. Alright? So I have R1, R2, R3, R4. And that becomes the voltage divider. So you can calculate V1 prime for the V out, okay? Or let's say V1 first, okay? So just keep doing that for V2, V3, V4 and add them together. So you can get overall V here. Make sense? Okay? Hope we can do well on Monday. We still have a lecture on Monday, do we? Okay, so we'll start op-amps on Monday. If you don't have other questions, do you want me to go through other problems on Monday? You can email me. Just email me what kind of problem you want me to go through on Monday, okay? I'm gonna do that. See you on Monday.